Here we have another question. Okay? Here we have another list of species. I identify which one's my strongest oxidizing agent, which reduction is occurring. Therefore, this is my cathode. Now, the silver ions, okay, is the strongest oxidizing agent, is aqueous. Therefore, we need a solid counterpart. Luckily, we were given the solid counterpart of silver ions, silver solid. This will be our solid electrode. This will be our cathode. Next from our list, we identify our strongest reducing agent, where oxidation happens, and this will be our anode. The zinc solid is going to be our electrode. It's already solid, so I don't need to use a replacement like an inert electrode like platinum or carbon. I just use zinc solid. So zinc solid undergoes an oxidation, meaning that it will lose electrons, and the zinc solid losing electrons will move the electrons through the wire towards the cathode. As the zinc solid is losing electrons, the zinc solid is transforming into zinc 2+ ions. So the zinc metal will be less, and there will be more zinc 2+ ions. So the anode loses mass because the solid turns into ions. The ions produced is more positive. So the product of the anode in this case is more positive. So this solution, this half cell is becoming more positive. Now let's look on the other side. The electrons is moving through the wire going to the cathode. So the electrons are going through this cathode electrode and will meet up with the silver ions. So the silver ions meeting a negative will transform into new products, silver solid. So therefore, the silver ions turned into silver solid. It might be coating the electrode, or the silver solid could be precipitating at the bottom of the container. So the cathode side gains more mass because the ions that were in solution is turning into a solid. To summarize, the anode loses mass. The cathode in this case is gaining mass. At this stage, we have not talked about the salt bridge, but for our purposes, the salt bridge is present to complete the circuit. And notice that the salt bridge information is not in the diagram because right now it's not in our cell notation. So let's summarize this through the equations that we have. So we have our oxidation half cell reaction. We have our reduction half reaction over here, and this is where our complete redox. According to our redox, our strongest OA is with our strongest RA, and this creates products, so therefore the reaction is spontaneous. As mentioned before, these containers are no longer neutral containers. The anode became more positive, and the cathode became more negative. So to keep the solutions neutral, anions needs to go to the anode, and cations need to go through the cathode. Now let's talk about the salt bridge and the spectator ions. The spectators are not necessarily written in the cell notation because they don't affect the reaction. So from table 7, we have the SOA silver ions, and we have the SRA, the zinc solid. The OA is above the RA, so this is a spontaneous reaction. To choose the spectators, we don't want anything reacting with the oxidizing agent, and we don't want anything else reacting with the reducing agents. So let's choose something in the salt bridge now. So we know nitrate is not on page 7 alone. So therefore it is a good spectator to use. But be careful if the solution is acidic. Then it becomes a strong OA, Notice that here we have nitrate and we have an acid, hydrogen protons, and it's even a stronger oxidizing agent than the silver that we have. But our solution doesn't involve any hydrogen protons, so we can safely use nitrates as a spectator. So now that we have a negative ion, an anion, we need to find a cation. In this case, we will choose a potassium ion, because if we see on page 7, potassium is near the bottom of the OA, meaning it's very weak. So to summarize everything, okay, in our salt bridge, we have potassium ions. We said that the anode became more positive and the cathode became more negative. If the anode became more positive, these nitrates then will start to move through the salt bridge to the anode side. The negative ion starts to move to the anode. Now we said that the cathode became more negative, so we need the positive potassium moving through the salt bridge towards the cathode to keep the solutions neutral. Again, you can choose other combinations as long as it doesn't react with our OA and our RA. Hope that helps.